This conference will now be recorded.
Hello students, very good evening. Today we are going to start a new chapter in the 11th standard, that is kinetic theory of gases. This is also a very important chapter for competitive exam as well as board exam, and there are many good concepts to learn and many good numerical problems are there to learn. Very nice topic this is. So kinetic theory of gas, actually the work on kinetic theory of gas or atomic theory of gases had started in 1600s or maybe more than that, like even before that. So in the introduction part we'll see what is this kinetic theory of gas, like what it deals with and who had contributed significantly towards this field. And finally we'll see, by knowing kinetic theory of gas, what are the physics we can learn, or what are the physical laws which can be explained with this kinetic theory of gases. So Boyle's, Boyle's law. So Boyle, scientist Newton, like great among the greatest physicists, Sir Isaac Newton and Boltzmann, then Charles Gay-Lussac, Gay-Lussac, then Boltzmann, all have contributed towards this field. Okay. So what is this kinetic theory of gas about? Actually, it it actually explains the behavior of gases based on the idea so it explains the behavior of gases based on the idea that a gas consists of a rapidly moving tiny particles which are called atoms. Moving atoms. Okay, or molecules. Rapidly moving atoms or molecules. So it deals with the behavior of the gases, considering a gas to be consisting of rapidly moving atoms or molecules. And this rapid movement is possible. See, in case of solid, we have seen that molecules or atoms, they are nearby and they have an interatomic force, right? Interatomic force, interatomic forces. So these interatomic forces in case of gas is neglected. Basically, for ideal gas, this interatomic forces is totally neglected. Otherwise, also for other gases, also this interatomic forces or interactions are neglected. Then only gas can continuously or rapidly move here and there. Okay. So in case of solid, atoms or molecules are placed very nearby. But in this case, gases and molecules are apart from each other, far apart from each other compared to solid and liquid. That's why the interatomic forces can be neglected, and then the atoms or molecules will be rapidly moving. They can freely move. So kinetic theory of gas was actually developed by kinetic theory of gas. So KTG, sometime it is written as KTG, kinetic theory of gas. It was developed by Maxwell and other scientists. Developed by Maxwell mainly, and obviously there are several other scientists involved in this. It gives molecular interpretation of, so it is actually, see, now we'll see what are the aspects it deals with or it can explain. Success of, we can say success of KTG, kinetic theory of gas. Kinetic theory of gas. Sorry. So what are the success? Number one, kinetic theory gives molecular interpretation of the pressure and temperature. So it gives molecular interpretation. As I said, any theory, when it is developed, there will be always some aim. That means it will be able to give us better understanding about various physical phenomena and try to make the concept clear to understand things. Okay. So in this case also, kinetic theory of gas, it can explain pressure and temperature from the molecular origin. Okay. So that's why it is said it gives interpretation molecular interpretation of pressure and temperature of a gas. Pressure and temperature, we know a gas molecules, like a gas has several number of molecules or atoms. They will be continuously colliding with the walls of the container and they will give certain pressure. So molecular, this kinetic theory of gas will give you perfect measurement, or it will help you to determine and interpret the pressure and temperature of a gas of a gas and is consistent with, see, this is again it, and it is consistent with gas laws, and Avogadro's hypothesis. Hypothesis. Okay, so these are the things. Second point is that it gives the explanation of specificity of several gases. It explain specific heat of several gases. Okay. It also relates some measurable properties. It also relates some measurable properties of gases such as viscosity, then conduction and diffusion, conduction and diffusion, diffusion with molecular parameter. That means these phenomena, this viscosity, conduction, and diffusion, these phenomena were further display relates with some with the molecular parameters, with the molecular parameters. Molecular parameters. Okay. So overall, this chapter will give you an introduction to kinetic theory, and in your advanced classes like in graduation and all, you'll learn this theory in detail. So let us start this chapter with some basic laws of gas given by Boyle, Charles, Gay-Lussac, and then we'll further learn the new things. So this may be new to not new to you, like say Boyle's law, Charles' law, and Gay-Lussac's law. These may be old for you, but still we'll discuss for our completeness of knowledge, and then we'll further proceed with the new concept. First of all, we'll see certain assumptions which are made in this kinetic theory of gas, and depending on those assumptions will derive most probable velocity, etc. Okay, in the next class maybe, but today we'll discuss these fundamental laws of gas given by Boyle, Charles, and Gay-Lussac, and we'll try to establish the perfect gas equation or ideal gas equation. And if time permits, we'll take up one or two numerical examples on this, like how to solve numerical problems based on these laws. So first of all, let us learn Boyle's law. So it is the fundamental gas law, and it was discovered by Boyle. Okay, Robert Boyle. His name is actually so discovered by Robert Boyle in 1662. Okay, it is the fundamental gas law. Okay, and what it states that the volume of a gas, the it says that the volume of a given mass of gas is inversely proportional to its pressure if the temperature remains constant. Temperature remains constant. Okay, mathematically it can be written as volume inversely proportional to pressure, I said, right, at constant temperature. Okay, and if we write in terms of equation, this would give you K by P, where K is a constant, and this we can write further, PV is equal to K, so K is a constant. Okay, so this constant, the value of K depends on few things like mass of the gas, its temperature, and the neat mass of gas, its temperature, and unit in which P and V are measured. Okay, now if we plot it mathematically, so PV is constant. If we plot this fact, in the PV diagram, sorry, in the PV diagram, where P in the vertical axis and V in the horizontal axis, so PV diagram looks like this. Okay, and here at T is equal to constant. You know this, you might have learned already in the previous class, 10th class. So if we plot this P and V, it will be like this. But if we plot 1 by V with P, then it will give you a straight line passing through the origin. Okay, it is like this. Okay, where this also T is equal to constant. Please note that this will be a straight line passing through the origin. Okay, this is PV diagram for Boyle's law, like when PV is equal to constant. Okay, at temperature T, when temperature T is equal to constant, PV is equal to K. So this is denoted by, or P is equal to K by V. This is actually denoted by this graph. Okay, all right. Now according to this Boyle's law, if if the volume, the pressure and volume of a gas is P1 and V1 initially, and corresponding pressure and volume, pressure and volume corresponding pressure and volume be P2 and V2 after some time or in the later point, then we can write P1 V1 is equal to P2 V2, or this implies PV is equal to constant. PV is equal to constant. So this is about Boyle's law. Now we'll go to Charles's law. Sorry, there will be no S further. Charles's law. So Charles's law was actually given by Alexander Alexander Charles. Alexander Charles in 1787. So it relates, actually Charles's law relates the volume volume of a gas with its temperature. With its temperature. Okay, that means it gives a relationship between V and T. Let us see what this law states. It is a nice statement. You should remember this. It states that if the pressure remains constant, it states that if the pressure remains constant, then the volume of a given mass of gas, then the volume of a given mass of gas increases or decreases by 1 over 273.15 times by this is fine, this much times of its volume at zero or absolute zero temperature. Volume at 0 degree centigrade, at 0 degree centigrade for each 1 degree, for each 1 degree for each 1 degree centigrade rise or fall of temperature. Okay, so it states that if the pressure remains constant, the volume of a gas, given mass of gas, increases or decreases by 1 over 273.15 times of its volume at 0 degree for each 1 degree centigrade rise or fall of temperature. Okay, if we write mathematically, we'll go to the next page. Let us continue Charles' law. Let us say V0 be the volume of gas, given mass of gas, volume of a given mass of gas at 0 degree centigrade. At 0 degree centigrade, according to Charles' law, Charles's law, the volume at Charles's law so according to Charles's law, the volume of the gas at 0 degree centigrade is given by V of T or V 1 degree. Let me write V of 1 degree. Let me write suffix as 1 degree is equal to V0 plus V0 by okay. So this would give you V0 whole into plus 1 divided by 273.15. Okay. So this will be the mathematical formulation. And now if we go for 2 degree centigrade, similarly I can write V0 into 273 this will be 2 divided by it will be 273.15. Okay. Similarly, if we go for Vt, then we can write V0 into 273 plus T. This is point divided by 273.15. Okay. So this is the final formula. What we can write is Vt is equal to V0 into plus T divided by now look temperature at absolute zero scale for 0 degree centigrade will be suppose T0 and that is 273 then T is equal to we can write 273.15 plus this small t then we can write this one V0 as T by T0. So from here we can say that V T by T is equal to V0 by T0 and this will be equal to constant, which implies that V versus we can write V is directly proportional to T. So this is actually Charles' law at constant pressure. At constant pressure, whatever we are doing for Charles' law, that is at constant pressure. So at constant pressure, we can see that the volume of a gas at constant pressure will be directly proportional to temperature. Okay, so that gone for Charles' law. Now we'll learn What is Boyle's law? Okay, Charles' law, if we plot, how does this look? See, we know Charles' law is going to be V directly proportional to T. Just a minute, I'm getting an important call. Sorry, I had to receive one call. Anyway, so we have discussed what is called Charles's law that relates the temperature and pressure, sorry, temperature and volume at constant pressure. So if we now plot V and T of a gas, since it is directly proportional, it will be like this. Okay, the curve will go through the origin and it will be a straight line, and throughout this curve pressure P will be constant. Okay, this is the graphical representation of Charles' law. Okay, now we'll go to Gay-Lussac's law. Actually, Gay-Lussac's law is similar to Charles' law, but it relates the pressure with temperature. Okay, let me write first Gay-Lussac's law. Okay, so it relates the pressure of a given gas, given mass of gas, with its temperature provided the volume remains constant. Remains constant. So I'm not writing the statement because this statement will be similar to this. In place of volume, we'll write pressure in this case. Okay. Let us write that, then you will understand. So Gay-Lussac's law is saying that, is stating that the pressure at any temperature or pressure increases with temperature. How it increases? It increases P0 over 273.15. So at 0 degree, sorry, at 0 degree centigrade, if the pressure is P0, then for each 1 degree centigrade increase or rise or fall of temperature will make the pressure, like will make the change in the pressure as P0 by this much. Okay, let me write itself. Okay, let me write the statement so that it it would not be confusing. So it states that if the volume remains constant, states that if the volume remains constant, then the pressure of a given mass of gas, the pressure the pressure of a given mass of gas increase or decrease of a gas, increase or decrease increases or decreases by 1 over 273.15 of its pressure at 0 degree centigrade, sorry, 0 degree centigrade for each 1 degree centigrade rise or fall of temperature. I hope you have understood this. Let us write directly the mathematical form of this. So we are continuing with Gay-Lussac's law. So it states, suppose I have pressure P0 at 0 degree centigrade when V is constant. Then pressure for 1 degree centigrade will be equal to P0 plus, it is increases by, okay, so P0 plus P0 over 273.15, that is equal to P0, so 1 plus 1 over 273.15, or we can write this as P0 whole into this plus 1 divided by 273.15. Okay, so if we write for 2 degree centigrade at constant volume, so it will give you 273.15 plus 2, okay, 2 degree centigrade, obviously this is in degree centigrade, divided by 273.15, this, okay. As you know, if I write for T degree centigrade for any arbitrary temperature P0, 273.1 sorry 0.15 plus T degree centigrade divided by 273.15. So this would, so this, you know, this is actually in Kelvin scale, this is absolute temperature. So we can write that as T, and this, if I write 0 plus 0 degree centigrade with this will be written as T0. So P into T, so what we get, Pt is equal to, so at any temperature, so let me just erase, okay, let me write it here itself. So this implies, see, Pt by T is equal to P0 by T0. So this is the pressure at 0 degree centigrade, and this is the absolute zero temperature, and this is at any arbitrary temperature the pressure of the gas, given mass of gas, and this is the absolute temperature. Okay, the temperature at which you want to calculate the pressure. So you can see Pt by T, P0 by T0, like that it goes. That means, this is giving you the direction that as we have written in case of Charles's law, V proportional to T. So in this case, P proportional to T. Okay, so it is saying that P proportional to T at constant volume, constant volume. Okay, so in other words, we can say Gay-Lussac's law that if the volume remains constant, the pressure of a given mass of gas is directly proportional to its absolute temperature. Okay, so this is the mathematical form of Gay-Lussac's law, and obviously if we plot P and T, it will go through the origin. It will be a straight line passing through origin. So this is P and this is T. Okay, and it here along the line at each point the volume remains constant. All right, so these are fundamental laws, like we have learned uh, Gay-Lussac's law. Before that we have learned Charles' law, Boyle's law. Now we'll try to establish the perfect gas equation or ideal gas equation. Okay, I'll just clean this. So ideal or perfect gas equation. Okay, see, to establish perfect gas equation, we'll just take up Charles's law and Boyle's law. What is Charles's law? Charles's law says that V directly proportional, inversely proportional to P. This is Boyle's law. Boyle's law. What about Charles' law? When, so in this case, temperature remains constant, and in case of Charles' law, if the pressure remains constant, then there is a relationship between. So here, temperature remains constant, and in Charles' law, there is a direct relationship between volume and temperature if sorry, this S will not be there. This happens when pressure remains constant. Okay, so if we combine these two, what we can write is V directly proportional to T divided by P. Okay, so this is what we can write, or in other form we can write PV directly proportional to T. Okay, so this you can write, and look here, or in other words, okay, let me just write this PV by T. This is equal to constant, right? This is constant, this is constant. So it is seen that for 1 mole of gas, the constant has the same value for all the gases. So I'll write this sentence. It is seen that for a mole, for 1 mole, for 1 mole of a gas, one mole of a gas, this constant, the constant is same for all the gases, and it is called universal gas constant. It is called universal gas constant. Universal gas constant. Okay, and this universal gas constant is actually denoted by R. So this universal gas constant, universal gas constant is denoted by R. Okay, let me just erase this portion. We have got already the relation. So PV, we had got PV by T is equal to constant. This constant is seen that this is like for a 1 mole gas, this constant value of the constant is same for all. That's why it is called universal gas constant and denoted by R. So if we denote it by R, then we can write here itself for 1 mole of gas, this is PV by T is equal to R. Okay. Now if we write this equation, so we get PV is equal to RT. This is very well known form of ideal gas equation or perfect gas equation, and this is for 1 mole. Okay, for 1 mole. Okay, so for n mole gas, what will be the equation? For n mole gas, what will be the equation? So for n mole, for n mole gas, we can write PV is equal to nRT. Okay, now I'll just tell you what is this mole. Mole is actually, see, suppose, okay, let me define it. Mole is given by mass of the gas, mass of given gas, the gas in gram, divided by the molecular mass, molecular mass, molecular mass. Suppose this is if I take, see, oxygen molecular mass is 32 gram. If I take 8 gram of oxygen, then what will be the number of moles? So in that case you have to write 8 gram divided by 32 gram. So this will give you 1/4. 4 moles. Okay, this is the value of number of moles in this 8 gram of gas. Similarly, if I take any gas 1 gram, and if the molecular mass is m0 gram, then 1 over m0, that will give you the number of moles. Now, okay, let me write PV is equal to nRT for n mole gas, and now we have got the definition of n mole, etc. Now see, I'll see if the gas is not given as a mole, if it is given for particular gram of gas, then we can write PV is equal to R R capital T. What is this R? See, this small r is actually uh, small r for 1 gram of gas. So this small r will be, so 1 gram of gas means the n is equal to 1 over m0. Okay, so if I put it here, so this r is actually capital R by m0. This is for particular, for 1 gram of gas. Okay, this constant can be written as small r into T. Small r means capital R gas constant over molecular mass of a particular gas. Okay, now see, there is another fundamental constant in kinetic theory of gas, that is Boltzmann's constant, that is generally written as Kb or sometimes simply K. It is given by universal gas constant divided by Avogadro number. Okay, so this implies R is equal to n A into Kb. Okay, these are the relationship between universal gas constant and Boltzmann constant. Okay, now look, if I write in terms of this equation in terms of Boltzmann constant, then what we can write? So PV is equal to, let me write this small n to be n, then NA Kb into T. Now what is this n in terms of Avogadro number? Suppose you have n number of molecules, and Avogadro numbers are there in 1 mole of gas. 1 mole of gas. So in place of small n, we can write this. So this, in terms of number of gas molecules, we can write the number of moles. So number of moles will be the ratio of number of molecules in particular amount of gas, or for a given mass of gas, to the Avogadro number, which is the number of atoms or molecule present in 1 mole gas. Okay, so if we put it here in place of this, so n divided by small as Na is equal to the number of moles, so into this Kb into T, which will give you Pv is equal to N, K, B and T. What is this? This is number of molecules. Okay, or Kbnt. So this capital N is the number of molecules in a given mass of gas. Okay, so we have finally got PV is equal to nRT, and another form in terms of Boltzmann's constant N Kb into T. This is the number of molecules of a given mass of gas, and this is number of moles of the given mass of gas, okay. So these are the two form of two well-known form actually. These are two well-known form of perfect gas equation or ideal gas equations. These are called ideal, sorry, ideal gas equation. Okay, so I'll stop it here for today. Next day we'll start with the assumptions of kinetic theory of gas, and then we'll derive most probable velocity or the velocity distribution in kinetic theory. We'll learn, and then we'll try to relate from there, like very RMS velocity of gas, most probable velocity, then pressure and other parameters of gas. Okay, so thank you for your patience. Bye for today.